We are back. We'll be discussing about uniformly accelerated motion. So what is a uniformly accelerated motion? By the term itself, uniformly accelerated motion, when we speak of uniform, so uni means one, so one form. It means that there's no difference. It's one and the same. So in uniformly accelerated motion, it's a motion of an object where the acceleration is constant. In any part of the observation period, at any part of the motion, the acceleration of the object remains the same. So in other words, the acceleration remains uniform. The acceleration is equal to a number, and that number does not change as a function of time. Even though time has passed already, and there's an interval of time that you have been observing the object, the acceleration of that object remains the same. So that's uniformly accelerated motion. And in uniformly accelerated motion, we have these kinematic equations or useful equations for us to solve for unknown quantities in problems involving uniformly accelerated motion. Now you have there 6 equations that can be useful in the problems that you may encounter. So the first one there is this one. You have average velocity. This is average velocity with a bar on top. So that's average velocity is equal to x over t. So x is your displacement or your position. In other equations, x there is also represented with the letter d. So again, that is average velocity is equal to x over t, where x is position or displacement and t is time. V bar is your average velocity. Now, the next equation here, A represents acceleration, while V represents velocity or final velocity minus initial velocity or V0. In other equations or in other references, you might see this as VF minus VI over T. And then you have here the third equation, you have average velocity. Again, take note that that is average velocity is equal to final velocity or velocity plus initial velocity over 2. And the next, you have position is equal to velocity plus initial velocity divided by 2 times time. So actually, all of these equations here, the 3 equations here, are derived from these 3 equations that we see on the left side. A combination and rearrangement of the variables there. And then another equation we have here is that position is equal to initial velocity times time plus 1/2 acceleration time squared. And the last equation that we have here is 2ax is equal to v squared or your final velocity squared minus initial velocity squared. So remember, what's important here is that you know the letters or you know what quantities the letters represent or what are these variables. Now, with all of these equations, now with the 6 equations, how will you know what equation to use? When you go into a problem or when you solve a problem, of course, you need to identify the given values. And as you identify the given values, you also have your unknown value or the one that is required for you to solve. So you need to plot it, all of the known variables and unknown variables. And looking into the known and unknown variable, choose an equation where all of the variables are there. All of the known variables and only one unknown variable. You cannot have 2 unknown variables in one equation because you cannot solve for that. You will need another equation for you to solve for it. But since we already derived equations, since we already derived equations out of these 3 here, then we can use these to solve for the variables that is unknown, provided that it's just one unknown variable in the problem or one unknown variable per equation that you will use in the problem. So let's take this Example, a train brakes from 40 meters per second to a stop over a distance of 0.1 kilometers. What is the acceleration of the train and how much time does it take the train to stop? What you need to do first is, of course, to analyze the problem or to make use of the keywords that are present in the problem. But one useful thing for you to do is to draw or illustrate the problem itself. So you have there a train. So for example, this is our train. Forgive my drawing. For example, that is our train. So of course you have wheels there. And then your train brakes to a stop. So for example, it stops at this point, which is 0.1 kilometers, right? As presented there in the problem. If a train brakes from 40 meters, then that means it starts from 40 meters because you have there from and brake. And when you brake something or when a running vehicle takes brake, then of course that will eventually stop. Therefore, our initial velocity here will be 40 meters per second. And since it will stop, your final velocity will be, or your velocity will be 0. Now, the question is, what is the acceleration of the train? For letter A, what is the acceleration? Now, what are our given values? Our given values are, of course, your initial velocity, which is 40 meters per second. And then you have the velocity, which is 0, or your final velocity. And then you have your displacement, or your position, which is 0.1 kilometers. Now, as you can see here, you have two different units, or I mean, you have two units of the same quantity, but in different expression. One is meter and one is in kilometers. So we need to level them both, or we need to have the same unit for your same quantities. So what we can do is we convert the 0.1 kilometers to meters, where 1 kilometer is equal to 1,000 meters. So you cancel that out. Then you get 100 meters. So that is our displacement, or the position of the object after it stopped, from the moment we observe the train, which is from 40 meters per second. So again, going back to what I've mentioned before, for you to be able to choose the equation to be used, you need to look into your known variables and the unknown variables. So you have initial velocity, final velocity, displacement, and acceleration. Now, what equation has these four variables? So the equation that contains these four variables is actually 2ax is equal to v squared minus v initial squared. If you have remembered our equation. So of course we need to solve for acceleration. Then we just need to get rid of 2 and x and transpose them to the other side. And that will be a is equal to v squared minus v0 squared over 2, which will give you, of course, your initial velocity, your final velocity here is 0 squared minus, that's v0 squared. Oops, let's substitute, that's 40 meters per second. So that's 40 meters per second. Then you square that over 2 times 100 meters. Now, since that is 0, then your acceleration will just be negative 40 meters per second squared over 2 times 100 meters. So keying in that in your calculator, so let's key that in. You have negative 40 meters per second squared. Remember, you do not include the negative sign if you square 40. You square first the 40 meters per second, and that's the time you add the negative sign. You have 40 meters per second squared, and then you put the negative, divided by 2 times 100. And that will give you a value of negative 8. Oops, why is it there? Negative 8 meters per second squared. Which means that the acceleration of the train is negative 8 meters per second squared. And remember, this negative here represents the direction of our variable, or of the velocity, or I mean of the vector, the direction of this vector, which is acceleration. So 8 meters per second squared going to the opposite direction. So now we have solved for acceleration. Next, we need to solve for the second question, which is, it asks us for the time. So what's the time? How much time does it take the train to stop? So from this position we have here, how much time will it take for the train to reach 0 meters per second? So again, we know, or you know, that our variables are initial velocity, you have final velocity, you have x, and then you have time. Now, what equation can we use? What equation can we use to solve for these, or to solve for time? What equation contains initial velocity? What equation contains final velocity? What equation contains x? And what equation contains time? So let's see. You have x is equal to v plus v0 over 2 times time. So that's the equation that we can use to solve for time. Now, since we just need to solve for time, then we need to derive an equation for time out of this equation. So deriving an equation for that, you will have time is equal to 2x minus v plus v0. That's now our equation. How did we arrive at that equation? So you can see here 2, transpose it there, it becomes 2x, and then you now have v plus v0 times time. You just transpose v plus v0 because they can be considered as one expression. You cannot just take out v separately and v0 separately because they are multiplied with time. So transposing that, it will be divided by v plus v0. So you now have time is equal to 2x divided by v plus v0. Substituting our variables or the values, you have time is equal to 2 times 100 meters over your initial, your final velocity is 0 plus you have 40 meters per second. So of course that's 0. That's just 40 meters per second. So you have 2 times 100. 2 times 100 divided by 40. And that means that the time is 5 seconds. So the time that it takes, or it took the train to stop from 40 meters per second with an acceleration of negative 9.8 meters per second squared is 5 seconds. So that's for our problem. Next, we have another problem. So a car accelerates from rest at 1.0 meter per second squared, that is squared, for 20 seconds along a straight road. It then moves at a constant speed for half an hour. It decelerates uniformly to stop in 30 seconds. To find the total distance covered by the car. So, looking into our problem, we have actually several parts here. If we are to illustrate that, illustrating our problem, we have a car. So let's say we have a car. There. We have our car. So that car starts from rest. So the velocity at this point is 0 meters per second. And then for 20 seconds, it accelerates from this position. It accelerates for 1 meters per second squared, 1.0, for 20 seconds. And then after that, after the end of 20 seconds, it then moved at a constant speed for half an hour. So let's say that's half an hour. The illustration, of course, is not to scale. Just take note of that. And remember that the velocity here is constant. There, constant velocity. And then after that, we have the motion of the car again changed because it then decelerated uniformly in 30 seconds. Again, not to scale. So we need to solve for the total distance of the car, or the total distance that is covered by the car. Looking into the motion of the car, you can actually have three stages. One, it accelerates. Two, it maintains a constant velocity, which means that when you say constant velocity, acceleration is zero. And then the third stage will be the car is decelerating. So from an initial velocity, it approaches now to zero, or it approaches to a stop, or it decreases because it decelerates. But according to our problem, our car actually stopped. So let's solve for the total distance of the car. So in this stage, we can solve for the distance of the car by resolving each of the distance separately. So for stage 1, and then stage 2, and then stage 3. So let's consider this as stage 1. We need to solve for the distance, right? Or the position of the car. So our known variables at this point is, of course, we know acceleration, which is 1 meter per second squared. What else? Let me just rewrite that one. Our unknown variable here is, of course, x. What else? Our known values. Since it starts from rest, then we know that our initial velocity at this point is 0 meters per second. And of course, we have the time, which is 20 seconds. Now, what is an equation that contains acceleration, initial velocity, time, and position? That equation is x is equal to initial velocity times time plus 1/2 AT squared. So substituting our values, x is equal to, remember, initial velocity is 0. So that's automatically 0 because any number multiplied by 0 is 0. Plus 1/2, your acceleration is 1 meter per second squared times 20 seconds squared. Remember to square time because as you can see here, time squared. So keying that in your calculators, so you have, of course, 0 plus 1/2, or if you add 0, then you can just actually take that out. So we can start with 1/2, or 0.5 times 1 meters per second squared times, you have to square that 20, of course. And that will give you 200 meters. So that is the displacement here, 200 meters. Now let's go into 0 point, or during the stage 2. Let's just make a division there so that we don't get lost. So for stage 2 still, we need to solve for your displacement. Now, since it's constant velocity, before we can proceed with the solution for stage 2, we need to know what's the velocity of that car. So how to know the velocity of that car? We need to solve at the end of, or we need to identify the velocity at this point. Here. Oops, there. At that point. Now, how do we solve for the velocity at that point? We can actually use the values that is in stage 1. So solving for the velocity there, what we just need to do is to use, of course, you have acceleration is equal to initial velocity, or final velocity minus initial velocity divided by time. And that will give you, or deriving an equation for final velocity, we need to derive an equation for this one. That will be final velocity is equal to AT plus V0. Now, since initial velocity is 0, then velocity is equal to AT, which will give you A is 1 meter per second squared times 20 seconds. Of course, we can cancel that, or you're left with meter per second. Then 1 times 20 is 20 meters per second. Therefore, the velocity at this point, so your velocity at this point is 20 meters per second. So if the velocity at this point is 20 meters per second with a constant velocity, then therefore the entire velocity at this stretch, or at this portion of the motion of the car, is 20 meters per second. And if both the initial and final velocity are 20 meters per second, so of course the velocity here will still be 20 meters per second because again, it's constant. Then therefore, your average velocity will also be 20 meters per second. Remember, the formula for average velocity is final velocity plus initial velocity divided by 2. So if we take this as our initial velocity, since we will start here, and then our final velocity is also 20, so 20 plus 20 is 40 divided by 2, it's still 20. Therefore, the average velocity is 20 meters per second. So how do we solve for displacement, or for the position, if we have your average velocity? Average velocity, remember, is equal to x over time. To solve for x, then the equation just becomes x is equal to average velocity times time. And we know time. But of course, we need to convert that time. So converting time, since it's hours, it's in hour, and we need a unit for time in seconds. So converting 0.5 hours, or hour to second, that is, let's rewrite some so that everything will fit. So you have 0.5 hour times 1 hour is 3,600 seconds. Then that will give you 0.5 times 3,600. Then that will give you 1,800 seconds. So you just need to substitute these values. Your displacement is equal to 20 meters per second times 1,800 seconds. So you're left with meter. So that's 20 times 1,800. That will give you 36,000 meters. Therefore, our displacement at this stage of the motion of the car is 36,000 meters. So let's divide that as well. Now we're down to our third stage. So we need to solve for the displacement again here. What is our displacement equal to? So looking at it, our initial velocity here is 20, right? Your initial velocity at this point is 20 meters per second, and then our time is 30 seconds. Now, what else? What are the other variables that we can get out of here? Remember that our velocity here is, again, 0 meter per second. Why? Because it stopped. As you can see there, it stopped. So since it stopped, then the velocity will be 0. So your velocity, or your final velocity, is 0 meter per second. So what equation can we use to solve for displacement if we have initial velocity, time, and final velocity? That will be what? Your x is equal to, let me write that, your x is equal to v plus v0 over 2 times time. Now, since final velocity is 0, then that's just v0 over 2 times time. So x is equal to, what's your v0? That's 20 meters per second over 2 times 30 seconds. That's, let me rewrite that one. That's 30 seconds. So keying that in your calculators, you've got 20 divided by 2 times 30. So you've got 300 meters. So you have 300 meters for the displacement for the third stage. But the question was find the total distance covered by the car. Of course, that will be from start to finish. So how do you solve for that? You just need to add the displacements or the distances in the three stages of the motion of the car. And that is 200 meters plus 36,000 meters plus 300 meters. And what will be the answer? So 200 plus 36,000 plus 300, that will give you distance total of 36,500 meters. So this is now our final answer. So 36,500 meters is the total distance covered by the car. So why did we need to chunk all of these up, or we need to divide the motion of the car into different parts? Again, our kinematic equations are for uniformly accelerated motion. So we need to dissect the motion of the car where you have same acceleration within that period. So between 20 seconds, or the motion in in the first 20 seconds of the car has uniform acceleration. It's accelerating. And then for the next stage, it has a different acceleration, which is actually zero. So we can solve for the displacement for that specific time using the kinematic equations that were given before or in the earlier slides. And then the third one, so now it decelerates, it now has another acceleration. And to be able to use the kinematic equations that was presented earlier, we need to have values of acceleration that are not changing, because again, those are for uniformly accelerated motion. So that's our lesson, or that will be it for uniformly accelerated motion. So I hope that you're able to get more insights or understand more about solving problems using the kinematic equations, specifically horizontal or one-dimensional uniformly accelerated motion. Now, for the next lesson, we'll be talking about the vertical one, or the special characteristics of uniformly accelerated motion vertically. So see you next time. Bye.